Hey everyone, how are you? It's Miss Lula. I hope you're doing great. Just coming at you today with a video on the kinetic molecular theory. Yesterday we talked about how scientists studied gases and how they made some observations about the behavior of gases. So then what happened was they put all those observations together to make a theory called the kinetic molecular theory, which essentially describes the behavior of the gases. Kinetic molecular theory might sound like something confusing. It's also known as the KMT, but actually, if we break down the words, it's quite simple. Kinetic means having to do with motion. You may have heard of the word kinetic energy before. Molecular, having to do with molecules, in this case, gas molecules. And so really, this theory is all about the movement of gas molecules. We can explain the behavior of gases if we are constantly thinking about the fact that gas particles are moving around. Now, like any theory, there are some limitations or some assumptions made to ensure that the theory holds true. Let's take a look at these assumptions and see if we kind of agree with them. So the first assumption of the kinetic molecular theory is that gases consist of small particles that have mass. Based on our conversation in our last video, we know that gas particles do have mass. We mentioned the basketball example where a deflated basketball will actually weigh less than an inflated basketball because the air in the basketball has mass. So this one we can pretty much agree on. Particles must be separated by relatively large distances. Okay, we've learned in the past that solids have this crystalline structure where atoms are super packed in and ordered. Liquids aren't as ordered but are still tightly packed. And then gases kind of have this going on where particles are, as mentioned, far apart from each other. So cool, we can agree with that one. Gas particles must be in constant, rapid, random motion. So that's saying that these particles are actually moving really quickly. Those little lines are supposed to show some movement, which I think we can agree on. And then it also talks about the fact that the motion is random, which means it's the particles are not attracted to each other. And so that's something we can assume to be true. There are instances where that doesn't hold true, but that's actually beyond the scope of our course. If you go on to AP, we'll learn a little bit more about that. But for our course this year, we can assume that all gas particles are not attracted to each other, and therefore they move really randomly and very quickly. And then gas molecules themselves have a negligible volume. Negligible means insignificant. And so what that means is if I have, let's say, a 1 liter container and I just have one lonely gas particle in it, the volume of the gas is considered to be 1 liter because this gas particle is going to whiz around all over here. The gas particle itself, while it might take up a little bit of volume, it's so insignificant that we assume it's negligible. We don't have to worry about it. The volume of the gas would be 1 liter because it's taking up the whole container. We don't have to account for that little dot there. And so that's what we assume to be true about the kinetic molecular theory. Okay. Now, gases exert pressure. This is what the kinetic molecular theory says. Gases exert pressure because particles frequently collide with the walls of the container in which they are held. So a classic example is a balloon. That's a container. And when you fill a balloon with gas, these gas particles exert pressure on the balloon by running into it, colliding with the wall of the container. So all gases exert pressure because they collide with the wall of the container. One thing to know is that when gas particles collide, they do what's called an elastic collision. An elastic collision is when no energy of motion is lost. I've written unlike a bouncy ball. So if you imagine one of those bouncy balls you can buy from like one of those quarter machines at the grocery store. If I dropped a bouncy ball, let's say I'm standing right here, this is my hand, and I drop a bouncy ball, boom, 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 and it hits the ground right here, okay? After that happens, it's going to bounce back up. But when it bounces back up, we know from our experience that it's not going to come all the way up here, because when it hit down here, it actually lost some energy, right? Some energy got transferred to the floor. So when it comes back, maybe it only comes here, and then it goes down and it bounces, and maybe here, down, and bounces, and then here and down and bounces, until finally it's like bouncing, and eventually it will stop, because every time it hits the floor, it loses some energy. That is an inelastic collision. Most things that we come in contact with have inelastic collisions. When they hit something, they lose some energy. Imagine if you're running around a room randomly blindfolded and you keep hitting the walls. Every time you hit a wall, you're going to get a little more tired. That is an inelastic collision. On the flip side, gas particles actually have what we call elastic collisions. Elastic collisions are things where sorry, 1 second, I'll be right back. Okay, sorry about that. I had to take a quick break just to deal with something. So we were talking about how a bouncy ball has these inelastic collisions, meaning that we lose energy every time it collides. But gases actually have elastic collisions, which means no energy is lost. So when a gas particle hits the wall of a container, or when a gas particle hits another gas particle, which might happen as well, like these two gas particles might collide, no energy is lost, and gas particles can keep moving and keep moving and keep moving, and no matter how much they're hitting the wall or hitting each other, they're not going to lose energy, which is why they're in constant, rapid, random motion. So gas particles have elastic collisions. The collisions exert a force which causes pressure. So anytime an object is able to exert a force, it can apply pressure, because by definition, pressure is force over area. But all we need to know is that those collisions are causing pressure. The more particles there are, the more pressure there is. That makes sense. Imagine a balloon with one lone particle whizzing around, applying some pressure, versus a balloon with 100 particles, everything whizzing around, applying quite a bit of pressure. So the more particles there are, the more pressure there is. That would make sense. Okay, those are some really expert drawings you're seeing. Okay, now the temperature obviously affects the pressure. We talked in our last video about helium balloons popping when they get super hot. So temperature is a measure of kinetic energy. It's really important to know that. Temperature is actually not a measure of heat in science. We use the word temperature in our everyday life as if it is a measure of heat, but in science, temperature is a measure of kinetic energy. That's one of the most important things that you need to learn today, that temperature is a measure of kinetic energy. Okay, and kinetic energy, of course, is the energy of motion. Here's some equations, but you don't really need to worry about those. I just threw them in there in case you remembered them, but they're not really important for our discussion here. What's important is that temperature is a measure of kinetic energy. So if we increase the temperature, the gas particles have more energy, right? So let's just think about that. If temperature increases, kinetic energy increases. That means the particles have more energy, which means they move faster. Their velocity increases. If they move faster, they're going to collide with the wall of the container more often. So, because temperature is a measure of kinetic energy, and kinetic energy tells us about the speed of a molecule, if we increase the temperature, we increase the kinetic energy, which means molecules are moving faster, which means there are going to be more collisions, which means pressure increases. And so that's just us, again, using the kinetic molecular theory to think about the motion of molecules. So the other piece is that when temperature increases and the molecules start moving faster, here's a slow molecule going to hit the wall of the container and apply pressure, okay? Versus high temperature, here's a really fast molecule, boom, it's not only going to collide more often, but it's going to collide with more pressure, with more force. So pressure increases when temperature increases because because temperature is a measure of kinetic energy. So if temperature goes up, molecules move faster. If they move faster, they collide more often, as well as with more force. And so that's why we can understand the relationship of pressure and temperature. We can look at this the opposite way. If temperature were to decrease, molecules would move slower, meaning they collide less frequently, and they collide with less force, therefore pressure decreases. Okay, cool. So this is our last slide, quick video today. This is the postulates of the kinetic molecular theory. The word postulates is just a fancy way to say the main points of the kinetic molecular theory. So this might be something you would put in notes. This is, just something that you would look up in the book. If you look up in your textbook, what are the postulates of the kinetic molecular theory? This is what the kinetic molecular theory says. Number 1, gases consist of large number of tiny particles that are far apart and relative to their size. Cool, we know that. Gas particles are far apart from each other and they're tiny. Collisions between gas particles and between the container are elastic. Cool, we know that. When gas particles collide, they keep moving, they keep colliding because they don't lose any energy. Great. 3, gases are in continuous, rapid, random motion, and they have kinetic energy. Awesome. We now know that the only thing that can affect the kinetic energy is the temperature. If we increase or decrease the temperature, we can get the molecules to move faster or slower. There are no forces of attraction or repulsion between gas particles. We talked about that. So gas particles move randomly because they're not attracted to each other. And the average kinetic energy depends on temperature. We talked about that. So by knowing these 5 things, which we've now talked about at length in 2 videos, we are going to be able to understand all of the behavior of gases. So looking forward to coming back to you guys tomorrow. Enjoy the rest of your day. Talk to you soon.